Welcome back. So we're picking up here in Chapter 11 talking about intermolecular forces, and we covered chapters 1 and 2, sections 1 and 2, and now we're going to look into section 3 and actually talk about it and the following in more detail. So the last slide we looked at here was about different phase changes and how we could explain using kinetic molecular theory. And remember, it's a balance between these intermolecular attractions between molecules, and the kinetic energy that they have, which is related directly to their temperature. So what are intermolecular attractions and how do they work? Well, essentially what we're looking at is, since we have electrons and protons inside these molecules, those electrons can be attracted or repelled from the other electrons or the protons that are in other molecules. And we know about covalent bonds and how some of those can be polar covalent and how some polar bonds can add up to make polar molecules, and so those all play a role into the different types of intermolecular attractions that you can have. So what are these attractions and how do they work? And we know they can range from being very, very small or non-existent nearly and like a noble gas, all the way up to being very, very strong and pretty much driving how that material behaves. Water was our example of that. So the stronger the intermolecular forces are, the stronger these forces are, the higher the boiling point will be of the liquid, and the higher the melting point will be of the liquid. And so that's an important key point that you'll want to put a star on, circle, put a box around it. The more intermolecular forces you have, the higher your boiling point will be, the higher your melting point will be. So what we're eventually going to want to do is be able to look at different molecules and identify this one has 2 of the intermolecular forces, this one has 6 different intermolecular forces that I can think of, this one doesn't have any, and so I know the one with the more intermolecular forces is going to have a higher boiling point, is going to have a higher melting point, and so I can rank those molecules just by visual inspection in terms of what their boiling point or melting point is, because I know about all the intermolecular forces that are happening inside of the molecules or between the molecules. So why do we have intermolecular forces in the first place? And Coulomb's law really helps us to explain that. So you know about the different electrical charges that are there, the negative charges and the positive charges, and we can model all that. If you'll remember in physics, we talk about, or perhaps you've talked about, you can actually calculate the amount of force and thereby the amount of energy associated between 2 particular charges or more. And Coulomb's law is the way that we do that. So a couple of important things to notice here. You've got Q1 and Q2. Those are the 2 separate charges that you're trying to find the force between. And then you've got this R in the bottom. Okay, here we're calculating the energy, but if you're calculating the force, it would be R squared. But notice the R, the distance between 2 molecules, plays a role into how much force or how much energy is needed or energy exists between those electrical charges. So if something is an ion, for example, a cation or an anion, then it's going to feel an attraction or a repulsion from another ion, depending on if it's the same or an opposite charge. And we can model how much force is felt between those by using Coulomb's law. And so we know also if there are polar molecules, they're going to have one end that's slightly positive, one end that's slightly negative, and that's going to affect how that one molecule, which is polar, interacts with another molecule, which is polar. And even some molecules that are nonpolar will still have intermolecular forces, because they still have electrons which are in all the molecular orbitals. And so the electron cloud of a molecule, remember those electrons are able to move around, and so they can create temporary, as they move, they temporarily displace one another. They can create temporary types of charges which can be repelled or attracted in other molecules and so on. So all these things play a role into the forces that are felt inside of molecules. So notice I have 2 water molecules here for you, and the distance between them plays a role into how much they feel, how much forces they feel between each other. and also the charges that they have. And remember, water is a polar molecule, and so we can think about it having a positive and negative end. And water also exhibits some other intermolecular forces, which we're going to talk about. And we're going to try to rank these forces to decide which ones play a larger role, which ones play a smaller role. And so as part of that, remember, if something has a larger charge, that means it has more attraction. So in this case, we have Q1 and Q2. If we have twice the charge on molecule 1, that'd be 2Q1. That means there'd be twice the amount of energy, twice the amount of force there. And so a larger charge on an ion means a stronger attraction. A larger charge, an electrical charge in general, means a stronger attraction or repulsion if it's an opposite charge. More distance between the molecules means a weaker attraction. They're further apart. Notice the R, which is the separation distance in this Coulomb's law formula, tells us that as R gets large, your force or your energy gets really, really small. So if they're pretty far apart, they can't interact with each other over a long distance. They're going to have weaker attraction for one another. So we want to think about how those charges work relative to one another and what sort of trends they make as far as how strong they are. So stronger attractions between atoms and molecules means more energy to separate them, higher boiling point, remember, higher melting point. And so a liquid requires more energy if it has more intermolecular forces to break it apart. Remember, these intermolecular forces are just forces felt between molecules. They're not the same forces like bonds are. Remember, in a covalent bond, you're sharing electrons to hold two atoms together, and that's what makes a molecule. Well, here we're talking about forces between molecules. And so the interaction that they have is not as strong as a bond, but it's still an actual attraction which plays a role in how a particular substance behaves and what phase and state it's in. So in general, the key point here is the higher the normal boiling point of a liquid, the stronger the intermolecular forces will be. And notice here we're using the word normal. We're talking about normal boiling points. That means you're under normal atmospheric conditions. Okay, so you know if you change the pressure of something, you can adjust its boiling point and so on. Well, what we're going to do is say the normal boiling point of all of these liquids correlates directly to the intermolecular forces that are felt. And that way we're comparing them all at the same pressure. So normal boiling point is kind of like standard pressure, 1 atm, so on. So higher the normal boiling point, higher temperature to get it to boil, means stronger intermolecular force. So I could show you two molecules and list their boiling points, their normal boiling points, and you could tell me which one has greater intermolecular forces, even if you don't know what those forces are at this point. So that's a great question. What are the different kinds of intermolecular forces you can actually have? And your book does a good job of listing this for you. Page 487 here. Dispersion forces and dipole-dipole forces and hydrogen bonding, ion dipole force. Those are the main ones we're going to talk about here in section 3. So those are the different types of attraction you can have. Now we're going to look at them all, each one at a time. Now the first one we said were dispersion forces. Sometimes these are called London dispersion forces, so you may have heard of them before. But essentially a dispersion force is a temporary polarity that happens inside of a molecule because the electrons are not distributed equally everywhere. Remember, those electrons are negative charges, and you have a lot of those negative charges on the molecule. And so as they're moving around inside their orbitals, temporarily they might move or shift to one side of the molecule or another, or more electrons might be on one side than the other, or so on as they're inside their orbitals. And this means you have an uneven distribution of that negative charge. So if all the electrons, which were in a perfect, distribution around the molecule, all of a sudden moved over to one side, then you'd have a slightly positive region, a slightly negative region, not a full polarity probably, but just a small temporary positive and negative separation created by these electrons moving, which is what we call a dispersion force. So those electrons kind of spread themselves out. We have dipole-dipole attractions. This is if you have two molecules that have dipoles, that is, if those two molecules are polar. Remember, di means two, And so dipole means two poles, a positive and negative. So you take water, which is a polar molecule. It has the slightly positive and slightly negative region, and so it has the dipole moment, and that dipole moment means it has a slightly positive, slightly negative region, and as another molecule comes close, that's also polar. It has the positive and negative regions, and so the positive and positives are going to want to repel, and the negatives and negatives are going to want to repel, and so these molecules will be more attracted to each other in a different orientation because of that dipole moment that they have. We call this a dipole-dipole attraction. And there's also these things called hydrogen bonds. Now, hydrogen bonds are kind of tricky because they have to have hydrogen atoms present, and they have to be attached to what we call an extremely electronegative atom. So they have to be a hydrogen atom attached to an electronegative atom. Remember, electronegative means like a desire to have electrons. So if you remember the periodic trend, the most electronegative atom is fluorine. And so if hydrogen is attached to fluorine, you have this condition satisfied, and you can have what we call a hydrogen bond intermolecular force. Now, it's not a real bond like a covalent bond or an ionic bond, but we still call it a hydrogen bond because it involves hydrogen in a very particular way. Okay, remember, it's not a chemical bond, it's an intermolecular force. All right, so let me show you some images of each of these different types. The dispersion force, remember, is a temporary separation of charge. So you have a region of the molecule that has a greater electron density and therefore a negative charge, and that means the other side will be sort of depleted of its electron density and have a more positive charge. This London force, or London dispersion force, or just dispersion force, is an intermolecular force that happens whenever a molecule has electrons. So, what molecules will have dispersion forces? The answer is any molecule that has electrons. What molecules have electrons? All of them. Well, practically all of them. So, all molecules and atoms will be able to have dispersion forces. So if they ever show you a molecule and ask you to list the intermolecular forces that are present, one that you can always list when you're working these problems is the dispersion force. So list all of the intermolecular forces that this molecule has. Immediately you know you can list a dispersion force. So when will some have a greater dispersion force or a lesser dispersion force? Well, we'll talk about that soon. So remember, it's just a temporary displacement of these electrons, and often we call that the polarizability, which is something we'll discuss in the upcoming slide. So here is the electrons in this molecule, and they're moving around frame 1 to 2 to 3, and notice as they are in their orbitals doing their usual thing as they normally exist, sometimes they're separated nicely, and other times they happen to be on the same side of the molecule, and that means it's going to be slightly more negative over here and slightly more positive over here. And in each of those situations, you're creating a separation of charge there on frame 3, and that's essentially what a dispersion force is. And so you can imagine if you have a situation where you have a liquid, or where these molecules are in contact with one another, you create this instantaneous charge separation. That was frame 3 we just looked at. Negative on one side, the negative on one side, the positive on the other side. And that just happened temporarily as the electrons moved, but now the molecule that was sitting next to that one that had the temporary distribution of the electrons, all of a sudden feels a slight positive charge next to it. And it says, oh, positive charge. All my negative electrons are attracted to positive charge. And so, boom, it moves some of its electrons over to be closer to that positive, which creates sort of this chain ongoing of the different ways that the electrons can be distributed inside the molecule. So these electrons are moving around inside their orbitals, and they're reacting to all of the charges that are around them. So if it happened at one molecule, then the next one can feel that charge separation and react to it, and its electron cloud can kind of move and shift, and these are dispersion forces. So how do we know when one molecule has a greater dispersion force than another? Essentially, it depends on several factors. One is what we call polarizability. And polarizability is a fancy word that just describes how easily the electrons can move around inside the molecule. Okay, that's kind of a simplistic way to state it, but polarizability is like the squishiness of the electron cloud. How easily can it be distorted? How easily can those electrons move to one side or another? That's the polarizability. So the higher the polarizability of a molecule means you can have more induced dipoles, more dispersion forces being created. And so typically that means if your molecule has a larger molar mass, and we're going to use that as an indicator so we don't have to count up all the electrons that are present, we'll just look at a molecule and say, does it have a high molar mass? If so, that means there are more electrons. If there are more electrons, that means there's larger electron cloud, there's more orbitals, more molecular orbitals, more places those electrons can be. That means there's an increased polarizability in general, and that's going to lead to stronger attractions. So one molecule will have a greater dispersion force than another based upon if it has a larger electron cloud, which means we can look at the molar mass to determine that. So I have two molecules, and I'm trying to decide which one has a greater dispersion force. I'm going to select the one with more electrons. How do I know which one has more electrons? I can sit and count them all out. Or I can just look at the molar mass of each of those molecules. The one with the larger molar mass is the one that has more electrons and therefore more dispersion force. So a higher or a stronger dispersion force. Now another thing that can play a role is the shape of the molecule. Remember, we're talking about electrons that live inside molecular orbitals of molecules. So if the molecule itself is large and extended, there's going to be more area those electrons can be spread out in, and that means more surface-to-surface contact between two of those molecules sitting on top of each other or moving around one another. And so more surface-to-surface contact means more charges can be felt. More charges can feel other charges in other molecules, which can lead to a larger induced dipole, which can mean stronger attraction. So how do you decide between two molecules? You can decide which one has the greatest intermolecular force of dispersion force, particularly, by looking to see which one has the larger molar mass, and then looking at the shape of the molecule. So you have to remember the three-dimensional shapes of all the molecules that we talked about in previous chapters, and determine a combination of those two things, which molecule then would have a greater dispersion force. So larger molecule, larger molar mass, more electrons, greater dispersion force, or more spread out, larger surface area, therefore larger dispersion force. So imagine two molecules that are spherical here, and there's only like one place they can interact compared to the situation before where they were flat and spread out. There's a lot of places to interact there, and so that leads to a greater dispersion force in general. So that's dispersion forces. And notice here is an actual comparison of the boiling points of these different atoms. Notice we're talking about noble gases. So what intermolecular forces will noble gases have? Well, we can say for sure they have electrons, therefore they have a dispersion force. Which one has a greater dispersion force? The one with the greatest molar mass. So we can immediately determine it's this one, xenon. 131.3 is its molar mass, which means it has more electrons and therefore a greater dispersion force. So if we didn't see this column of boiling points, we would immediately be able to say xenon has a higher molar mass, therefore has a higher dispersion force. That means it has more intermolecular forces than these other noble gases, and it should have the highest boiling point. Even if we don't know what the number is, we know it should have the highest boiling point. And so you see a correlation here. Larger molar mass means a larger boiling point. So, since noble gases don't display any other types of intermolecular forces, it's directly related to the dispersion force that they feel. It's a pretty interesting table there, 11.3, which shows us that. This table is on page 488 at the bottom left-hand side of the page there. Now, here's a relationship between boiling point and molar mass of nonpolar molecules. That means they're not polar. They don't display other intermolecular forces. It's really just dispersion force. And notice the period is increasing as I move to the right, and therefore the molar mass is increasing as I move to the right. We're plotting the boiling point of noble gases, the boiling point of the halogens, and the boiling point of these molecules combined with 4 hydrogen atoms, so like methane and so on. And you'll see in this case that the noble gases have a lower amount, but the values get higher as I move across the period to get to higher molar masses. And you'll notice that the trend is more steep when we're plotting the halogens here. Halogens are able to have a large molar mass and a large change between them, but in each case, as the molecule or as the atom gets larger, you have a greater dispersion force and you have a higher boiling point. So it matches the trend of what we would expect. Okay, here's straight chain alkane molecules. Now, if you'll remember, alkanes are just connections of hydrogen atoms. And so methane, we have one, did I say hydrogen atom? I meant carbon atoms. So we have one carbon atom in methane, we have 2 in ethane, 3 in propane, 4 in butane, 5 in pentane, and so on and so forth. So our chain of carbon atoms is getting longer and longer and longer. That means the surface area is increasing, and so we can compare how the surface area works. Notice the molar mass is getting higher as I move down, which means the dispersion force is getting larger because there's more electrons in general, but also as the chain grows, there's more and more surface area in general. So we expect then that the boiling points should be going up, the melting points should be going up, and that's exactly what we see in this situation. Here we're comparing the surface area of these different molecules. Notice the trend, higher boiling point, higher molar mass, higher surface area, so on. So it's a really great trend which helps us to wrap our mind around this particular intermolecular force. Larger area for interaction between molecules leads to a greater dispersion force, as you can see in the case of pentane here, compared to neopentane. Even though they have the exact same molar mass and same number of electrons, this one that's in a long chain situation has a greater surface area and therefore a greater dispersion force than the neopentane does, and so it should have a larger, N-pentane should have a larger dispersion force, intermolecular force. So we predict its boiling point should be higher, indeed 36.1 compared to 9.5. And we can explain that based upon the dispersion force. Okay, actually you can see the plot and the comparison here. In each case, the surface area is larger in the n-Alkanes compared to the isos, and so the n-Alkanes constantly and always maintain a higher boiling point. So let's try a little practice here. Choose the substance in each pair with the higher boiling point, CH4 or C4H10. Okay, in A, part A here, notice C4H10 has more electrons and a greater molar mass, so it should have a larger dispersion force, and it also has a larger surface area. So of these two, we're going to pick this one, larger surface area and greater molar mass. Now of these two, this one, they both are C6H12, and so that means they have the same molar mass, and we're just going to compare their surface area. So notice this one's a long, straight, kind of tubular shape, and C6H12 is kind of a ring shape, almost sort of like a donut, but kind of like a hamburger bun. And so a hamburger bun shape here would have slightly more surface area, so we would predict it would have the higher boiling point. So we picked those two over the others. Oops, what happened to my words? Oh, there they are. Okay. So dispersion force is playing the role here because we don't have any polar molecules. And we're thinking about molar mass, and we're thinking about surface area. Next, we want to talk about dipole-dipole interactions, but we'll do that in the next video.